First of all, hello everybody, and thanks to the organizers for letting me talk. You can see that we'll talk about cross products as compact quantum metric spaces. And what I would like to do is first like to present to you a construction by Hawkins, Belsky, White, and Zacharias, who construct certain kind of well-behaved spectral triples and cross products. And then I will talk about whether or not this construction will induce a compact quantum metric space structure of the corresponding cross product start for us. So yeah, let's first talk about spectral triples and cross products. Maybe, well, before I talk about this, let me maybe start with an example. So let's take a finitely generated discrete group. So all groups in this talk will be finitely generated in discrete. And on this group, I would like to consider a proper length function L, which is from the group in positive real numbers. This should be a proper length function. What does it mean? So a length function, well, it's a function from G to the positive real numbers, which satisfies that L of G is equal to 0 if and only if G is the identity element. We want L to be invariant under taking the inverse in the group, and we want to have some analog to the triangle inequality. So that's what a length function is, and the proper length function is a length function for which, if you look at the balls, different radii, you want these to be finite. So we are in this picture. Okay, and then out of this data, you can build a spectral triple. I think this goes back to Con, this example, which looks like this. So you take the group algebra, and you view this as a star subalgebra of your used group system algebra, which is faithfully represented on L2 of G, and you take as your Dirac operator the operator ML, which of course I'll have to tell you what this ML does.
Okay, go ahead.
Okay, maybe. So this ML takes an orthonormal basis element delta G, L2 of G, sends it to L of G plus delta G. Okay, so this is a nice example, and I would say it's a natural question to ask for something which looks kind of similar on the cross product level. So this is what I want to talk about next. And let me fix the setting. So again, let's take a discrete finitely generated group. This all C star algebras will be separable and unital. What else? We want to have an action alpha of the group G on the C star algebra. So this is an action. And we want to have, again, a proper length function. Right, and I guess so we want to build spectral triples and cross products, so I guess it's natural to assume that we start with a spectral triple on the C star algebra A we start with. So let's take this as well. Let's note the star algebra of smooth elements with curly A. Let's note the corresponding Hilbert space by HA corresponding Dirac operator by dA. So this is expected to go on A. So what to do next? So of course now I'll have to tell you how the Dirac operator, the corresponding Hilbert space, and the corresponding star subalgebra should look like. For this, we do the following. We define an operator D in the following way. So this operator should act on H plus H, where H is supposed to be tensor product HA with L2 of G. The operator D should look like this. So we have zeros on the diagonal. So we have a tube rating. Here we take A tensor 1 plus I times 1 tensor ML. And up here, take the adjoint. This is the operator that we consider. Now I'll have to specify star subalgebra as well. This is also quite natural, I guess. Well, it's a natural choice to look at, well, let's say, compactly supported functions on G with coefficients in curly A.
Spectrally, you start with this R.
Sorry?
Spectrally, you start with this R, or even.
It is odd, yes. Yes. Yeah, so as I said, we'll look at all sums of this form, AG times lambda G, where these lambda G's shall be the Laplace representation operators. And these AG's are coefficients curly A. Well, and we want almost all of these AG's to be 0. Almost all G. Okay, and this defines a nice star subalgebra, the cross product star algebra of A IG. Okay, so now the natural question to ask for: does this construction give us a spectral triple on the an even spectral triple on the cross product star algebra? This question has been asked by Hawkins, White, Skarsky, and Zacharias as well, who proved the following. So, Hawkins, Skarsky, White, Zacharias. This was, I think, in 2013 or 14, something like this. They imposed the following extra condition. So we additionally assume that the action alpha is in a certain sense well behaved. In the sense that alpha is so-called metrically continuous. Continuous. I should of course tell you what this means. So this means that the action preserves the star algebra A, and commutators should not explode in the sense that if we take the supremum over all H and G, we look at norms of commutators of the form dA with alpha H of A. then this should be smaller than infinity on A star algebra and G. So this is our extra assumption. And then what they prove is that in this case, this triple CC A D is an even spectral on the cross products to start. Alright, so this is quite nice. Kind of have a nice looking construction of even spectral triples and cross products. It kind of looks like the example from before. And then I would say a very natural question is now to ask for, does this spectral triple induce a compact quantum metric space structure on the cross-proxy star graph? And this question was also asked by Hawkins, Galsky, White, and Zacharias in 2014. They answered this question for Z with the standard generating set, but yeah, beyond this, I think nothing is known in this context. Okay, let's approach this question. So let's call it compact quantum metric spaces. Maybe I should say one or two words on the example from before. So in the groups algebra setting, certain things are known. As far as I know, in this setting, the triples induce compact quantum metric spaces for instance, word hyperbolic groups. Then Rachel has a paper on the case where the G's are just Z to the N's. And this was later extended to well, essentially polynomial growth groups. But I think beyond this, not much is known. Okay, so let's formulate a question. So if a pair consisting of A LDA with the Lipschitz semi-norm LDA defined to be the operator norm of the commutator of A with DA is a compact quantum metric space, then is corresponding cross product corresponding which is one as well. And maybe I should recall what a compact quantum metric space is. So this, at least in our context, this means more space. Well, using those LDs, you can define a metric on the state space, which is star algebra. Then we say if the pair gives you a compact quantum metric space, if the following holds. So using these LDs, we can define a metric in the following way. So this is supposed to be the supremum for all A's equal A such that smaller than or equal to 1. Then we look at the distance of phi of A by prime of A. This induces the weak star topology. On the state space of the system algebra A that we speak of in context. So those who were here last week will remember this definition, but yeah, here it is again. But you can reformulate this property in the following way. So this is equivalent, and this is essentially to reform in 1998 in the following way. So this is equivalent to the image of the set S consisting of all functions x in CCG A, for which the following two norms dA tensor 1 commutator with x smaller than or equal to 1 and 1 tensor ML comma x is a norm smaller than or equal to 1. If the image of this thing is totally bounded in the quotient space. So we take the cross-product system algebra, we mod out C times 1, and then we look at the induced topology in here, and at the image of this thing in here, and we ask for is this totally bounded or not. So, yeah, this condition of the weak star topology being induced by this thing looks a little bit annoying, but well, Riefer came up with a couple of equivalent conditions. So this is quite nice, and this is, I guess, what you usually use to show that something gives you a complex quantum metric space. Maybe I should hurry up a little bit. So, well, does this hold? Do we get compact quantum metric spaces on cross-product algebras in this way? And one idea that you could try, which already appears in one of Riefel's papers, the following. Maybe let's take an element x in S and look at the commutator, the second commutator up here. So let's look at what one tensor ML commutator with x, what this really is. So this x looks, well, like the sum of these AG's lambda g's. Then we can rewrite the commutator in the following way. So we have one tensor phi GL. I'll tell you in a second what this phi GL is, times the coefficient AG times the left regular representation operator lambda g. And this operator here does the following. So it takes orthonormal basis element in this takes an orthonormal basis vector delta h and sends it to the following. So L of h minus L of g inverse h times delta h. So this is really an operator in L infinity of g sitting inside V of L2 of g. Right? And now the idea is, so if you maybe for a second forget about operator valued AGs and just think of complex valued coefficients, and somehow this looks like a cross product, right, over of G with some suitable coefficient algebra, which is which you can make precise. So this will be the continuous function on the so-called Torah function convectification of G. I will not go into details. But okay, so this has the structure of a cross-product system, and then the idea is to project down from this bigger cross-product system algebra onto the reduced group system algebra sitting inside there. So essentially, in the cross-product setting, you do the same. Here, these sums will look like some double cross products or so, but the idea is the same. You project down by constructing suitable maps, which send you back into your original cross product to start. This is a little bit vague. That's essentially what you do. So that's number one. Number two is that you want to project down in a certain, in a certain way. You want to have lots of possibilities to do so in order to not lose too much information that you get from this inequality here. And this is the motivation for the following lemma and definition. I should have prepared a joke for working the board. So then, finished. Okay, so let's proceed. So as I said, from what I explained to you in a little bit vague way, you might come up with the following lemma and definition. So what to do? So let's maybe first of all take some notation. Let's denote by PG the following. First write it down and then explain it. Okay, so in G, you can consider the commutator subgroup. You can mod it out. And since we assume that G is finitely generated, this group, which is abelian, will also be finitely generated, right? And therefore, it will decompose as some torsion-free part and a torsion part. And then what I want to do is I want to map G to G mod the commutator subgroup, and then project down to the torsion-free part of the group. So this is this PG. What else? And I want to have an invariant mean on L infinity of G. So what is an invariant mean? That's a state on L infinity of G, which is invariant under the canonical action of the group G on L infinity of G. Right? So in particular, I assume that the group G is amenable. And then by using these ingredients, you get a well-defined group homomorphism, which looks like this. So that's denoted by mu L hat, which goes from the image of PG to the real numbers, which sends an element of the form Pg of G to mu of phi GL, where these phi GLs are these maps from before. And well, it's really easy to see that this gives you a well-defined group homomorphism, because these, if you look at these phi G maps in more detail, you will see that they satisfy some kind of one co-cycle condition. And by combining this with this invariant mean, well, you get that you have a group homomorphism. So this is pretty easy. Now comes the definition part. So as I said before, we want to have lots of different ways to project down from this element here onto the cross-product algebra. I will formalize this in the following way. So I will say that the group there consists of G and the length function L is separated if the set, well, you can write every group homomorphism from the image of PG to R as a linear combination of these mu hat L maps. Right, so this is quite a strong condition. So many groups will not satisfy this condition, but there are examples of groups which do. And now comes the theorem, which tells you why this is relevant for this question from before. Namely, you can show that if, in the setting from before, again, you have a group, you have a length function, and so on. If you find some finite index subgroup in G, such that the restriction of L to H is separated, or some finite index subgroup H in G, what else? You also need, so this theorem holds in greater generality, but let me restrict to this case. I also want to have that the commutator subgroup of H is finite, which is also quite a strong condition. Then this pair from before, so the cross-product system with this LD gives you a compact quantum metric space. So this is nice, right? So for these types of pairs, we can get compact quantum metric space structures. Maybe, yeah, in these I should mention one example. Right? Even though my time is almost up. So as I said, these are strong conditions, and you might ask, well, are there even groups which satisfy these conditions? The answer is yes. So if we take G to be equal to Zm, i.e. integer lattice, and we take L to be a word length function, with respect to some finite generating set, then you get that the corresponding pair GL is separated. And this in particular implies, with this theorem from above, that if you take G to be a virtually abelian group, then you will get a compact quantum metric space structure. And yeah, originally I planned to sketch the proof of this, which is not super difficult, and which uses some cool results from metric geometry. Yeah, I guess I'll skip this. So thanks for listening.
Are there questions, comments? Nadia?
Yeah, so the conditions look so on the group. So on the actions, do you still have any of the conditions you had before, or no?
Yes. So the conditions on metric continuity and everything that I mentioned before. It's also part of the theorem, but to make it short, I didn't mention it.
Right. And I guess somehow then you could just have any system yeah. Do you think you can go back? Probably a very strong condition. Yeah, no. There.
If I remember correctly, if you have a finitely generated group whose commutative subgroup is finite, then the theorem of Schur says that the center has finite index. So this is exactly what the groups. That you agree?
Yes, probably. Yeah, as I told you.
So this is exactly the class of virtually V groups, G.
Yes, so as I told you in the paper, this theorem is formulated in a more general way, but yeah.
But this theorem is for virtually V.
Yeah.
I have two. The first one is a comment. I think this theorem of Hawkins, Skalski, White, and Zacharias, it's an example of the unbounded Kasparov product.
Mm-hmm.
It's just how we should look at that. And then I was wondering, so would it be reasonable to expect that, if you know that the scalar case holds the cross product is also a geometric space? Like if you know that, if you just forget about the algebra, then you have a universal spectral triple. If you know that this is a spectral metric space, I mean, would there be some way of then concluding that this automatically holds for cross products as well, assuming that you have spectral triples up there? Because it seems like your condition in your theorem is only on the condition on the group and the length function. Yeah, it's nothing about A.
Yes, so what is
it's a spectral triple.
Yeah, so you're right. So this condition, I can maybe say one or two words about the proof. So this condition helps you to deduce that for every element x coming from this set S, you can approximate all these elements in kind of a uniform way by something which is finitely supported on G plus something small.
Well, I mean, you have the same problem if you just look at the group itself without.
Yes, indeed.
Okay, so maybe something to think about.
I'm not quite sure if I know what you mean.
Yeah.
So this definition helps you to get in the finitely supported setting, and then you use the second condition to prove that that then this set S is totally bounded. But you really need this.
Yeah, sure. But maybe we can talk about it.
Yeah, maybe. Okay.